advances on the solution of nonlinear least square problems. Sandra?
I'm already. Thanks, Paulo, for the introduction. Thank you for being here. Let me start congratulating Alfredo for his birthday and thanking him for the leadership in Brazil, his important role for us. Indeed, we didn't collaborate, but I have an indirect collaboration with former students of Alfredo, I mean academic descendants of him, and that's the reason I've chosen this subject to talk to you today. So I should also acknowledge my institution and the Brazilian agencies that gave support to our research. So this is the outline of my talk. I will start with some notation, the problem, and some assumptions, then a brief timeline, and then develop a little bit more on these 4 topics. Then I gave our final remarks and a few references. So basically, this is the problem we are addressing. It's pretty standard and classical, the nonlinear least square problems, and I will address it by NLS. We have a residual function that has much more components than variables, is usually associated with an overdetermined system of equations. And because we are assuming that the function is smooth, we have a particular and nice structure for the gradient and for the Hessian matrix. This is the notation for the Jacobian. And in this case, if we have a solution for the set of equations, then we see that due to the structure of the Hessian, at the solution, just the first order part of the Hessian takes part. And in case the Jacobian is full rank, then this x star globally minimizes the function, the nonlinear least square function of this unconstrained minimization due to the second order sufficient conditions. And this is the so-called zero residual full rank case. As usual in nonlinear programming, we address this unconstrained minimization problem by means of an iterative scheme. And the fastest is Newton's method, in which the linear system to be solved has the Hessian as the coefficient matrix. Now, because of the structure of the matrix, in case we have the zero residual, then close enough to the solution, this part of the Hessian does not play an important role, and then this motivates the Gauss-Newton system, in which just the first order part of the Hessian takes part. Of course, for this system to be well defined, the Jacobian must be full rank, and in this case, when we have zero residual and the Jacobian has full rank, Gauss-Newton is as good as Newton. I mean, it enjoys the quadratic convergence of Newton. Okay, but having full rank is a pretty strong assumption. So to weaken it, we may make a shift in this matrix, in this first order part matrix of the Hessian. And this shift being non-negative, we would like to be sure that we have a positive definite matrix there. Anyway, controlling this parameter that is called the Levenberg-Marquardt parameter is an issue, because if it is too small, then the U condition of the system might not be properly correct. On the other hand, if it is too large, then it may, the direction obtained will be very gradient oriented, and then you lose the speed of the convergence. So in this case, when we have rank deficient for the analysis, an additional and important assumption is the error bound condition. And when we consider problems with zero residual, we define the solution set as this one, and we say that the norm of the residual function provides an error bound for the set of equations if there is a constant that such that this condition is satisfied, so that the norm of the residue provides an error bound for the distance to the solution set. This constant is pretty much in charge of adjusting the units, the units of the domain and of the image space. Okay, now that we have seen a little bit of the terminology and the definitions, then I can talk about, give you a brief timeline with a few works. So no doubt, Levenberg and Marquardt are the most important works in this area, and I just include the not so well-known work of Morrison, that is in time is just in between of them, and he also addressed this dumping globalization strategy. In this list that dates from the last century, you recognize important and well known names in our community of nonlinear continuous optimization. And most of the efforts in the very beginning were related with derivative-free methods and structured quasi-Newton methods. Now, in the beginning of this century, in the first 10 years, we should also notice some works relating to problems with singular problems, problems where the Jacobian does not have full rank. Also, worst case analysis started to become fashionable, huge problems, and problems with some more structure. And in the last 10 years, we have also continued analysis with respect to problems with singular assumptions, and as well problems with simple bounds, and the complexity analysis continues, and procedures for ill-posed problems. So continuing on this list, I have selected 4 particular contributions with my co-authors that I will acknowledge along my presentation. So this first work was developed together with Douglas Gonçalves, and it concerns a spectral correction for the Gauss-Newton model. So I just recall the Hessian here, and we consider the sequence generated by the method and take the part of the Hessian that contains the second derivatives, and our idea was to build a scalar matrix that approximates this part. So these sigmas are computed with the Barzilai-Borel-Raidan philosophy, so that the matrix Sk is defined as a scalar matrix, and alpha k is defined in this way, or in matrix form in this way. So actually, this parameter has a second order correction role, and it's sign-free in contrast with the Levenberg-Marquardt parameter that it has to be non-negative. So the algorithm is quite simple, so I just present it here. We start with a point, we initialize this parameter, then we have to solve the Gauss-Newton corrected system, set our step, update the parameter, and goes on. So in case our residual functions are quadratic, then this matrix S, the expression of our parameter is indeed a Rayleigh quotient for the matrix Sk, so that alpha k is in between the smallest and the largest eigenvalue of this matrix that we are going to denote by sigma. And we are going to denote by lambda k min and lambda k max the smallest and the largest eigenvalues of the Jacobian transpose Jacobian. We use the same notation for a stationary point x star, so that the eigenvalues corresponding to the matrix S star are denoted, the extreme eigenvalues are denoted by sigma, star min, star max, and lambda, star min, star max for this matrix here. So to provide you a better idea on our result, I just recall here the theorem for Gauss-Newton as stated and proved in Dennis and Schnabel's book. So the assumptions are that the nonlinear least square problem has a twice continuously differentiable function. The Jacobian is Lipschitz, bounded, and the stationary point is such that the Jacobian is full rank, and this key condition is satisfied. In case all these assumptions are verified, then the sequence generated by the Gauss-Newton method, the local Gauss-Newton method, is well defined, converges, and satisfies these two conditions upon the error. So I should mention that this parameter sigma is very important because it carries not only the size of the residuum, but also the nonlinearity of the problem. Look that if we have a zero residual problem, then sigma is zero, and indeed this part is removed of this condition, and we observe the quadratic convergence of the problem that has full rank and zero residual. Now, if the residual is not zero, then we see that the Jacobian takes a very important part in the analysis. And indeed, we have to have this bound. Lambda has to be below the smallest eigenvalue of J star transpose J star. Otherwise, we don't have the contraction, and then we don't have the convergence of the iteration. Okay, so really, what happens to that vector that appears in the key condition of the theorem? It's indeed an approximation for the action of S star upon the error. And when we have a quadratic problem, then this approximation turns into an equality. In this case, we can see that sigma is indeed the true norm of the matrix S star. And then we have actually the condition of the theorem is that the spectral radius of this matrix has to be below the smallest eigenvalue of J transpose J star. So our analysis demands these two assumptions. This first one that connects the eigenvalues of both matrices, and also this one that says that the length of the interval that contains the extreme eigenvalues of S star has to be bounded in this way. So whenever matrix S star is not positive definite, our two assumptions are essential for obtaining the condition of the theorem. But on the other hand, if S star is positive definite, together with this condition, we obtain our assumptions. So we see that in this circumstance, our assumptions are weaker. So here is the proposition that establishes the well-definiteness of the algorithm, and also we have the linear convergence. If we compare these expressions with the original Gauss-Newton theorem, they look more complicated, but I should stress that they are smaller than the original constants of the linear convergence of Gauss-Newton. So an example to illustrate the ideas. Here we have the functions that assemble the residual functions. This example is nonlinear. It's an example where the solution has not zero residual. And we are comparing the performance of Gauss-Newton against Gauss-Newton with the spectral correction. This problem has a singular first-order part of the Hessian. And because of that, as the sequence tries to approximate the origin, that is the stationary point of the problem, then Gauss-Newton gets so ill-conditioned that it diverges. We start from this point. On the other hand, if we start from the same point with the spectral correction, in 9 iterations, we reach this stationarity to the level of 10 to minus 8. So just a brief summary on this contribution. We have devised a simple spectral correction strategy for the Gauss-Newton method. It ensures convergences in cases that Gauss-Newton might not converge. And whenever the matrix S star is positive definite, the linear rate convergence is better than Gauss-Newton. Now, our second contribution is a joint work with Elisabeth Caras and Bernard Zweiter. And we have devised algebraic rules for computing the Levenberg-Markov parameter. Our assumption basic is the Lipschitz continuity of the Jacobian. Here is the expression for the Levenberg-Marquardt step, and we would like to have an expression for mu k such that this should be as large as possible and accepted in the sufficient decrease condition with step length 1. So just a summary of the basic ideas behind our expressions. I just dropped the index k for easy reading of the expression. So I recall here the linearization, the traditional linearization bound inequality for the residual function. We have also the expression for the Gauss-Newton step. And we just obtain two independent bounds for this based on the problem properties and features. And I should just mention that PR is the projection on the range of the Jacobian. And based on these two bounds, and also on this expression that tell us the prospective evolution of our objective function, of nonlinear least square objective function, the idea is to impose that this should be non-positive and obtain from this bound expressions for mu. So indeed, this is the one obtained from this bound. This is obtained for the other bound. And because of that, we are sure that the sufficient decrease is obtained with step length 1. Notice that we are actually using the Lipschitz constant of the Jacobian in these expressions. So basically, whenever we are not stationary, if we take a Levenberg parameter greater than this mu minus, we are sure that this direction is of descent, and it's going to be accepted by the Hermitian line search with step size 1. We also define mu plus and mu j that are going to help us in the definition to obtain larger values for mu. So putting all this together in an algorithm, we basically, what we have to do is to set the parameter among these two values. We indeed use this minimum between mu j, the previously defined, and mu plus. Then the line search helps us to adaptive update the Lipschitz constant that is not usually known. So we have this procedure that also defines the actual and predicted reduction accordingly to monitor this evolution. So with all this together, we managed to prove that the algorithm is well defined, that I mean this line search finishes, and it is globally convergent. And up an error bound condition, assuming that the problem has 0 residue, then we have proved also quadratic local convergence. So just summarizing this contribution, we have these algebraic rules for choosing the Levenberg-Marquardt parameter. These rules are based on the Lipschitz continuity of the Jacobian, and they combined with the line search allowed to have large directions that are of descent and are usually accepted with a line search just with the step length 1. Whenever the Lipschitz constant is available, then the full steps are really accepted. Otherwise, it is dynamically updated, as I showed you in the algorithm. We obtained the quadratic convergence under an error-bound condition. And although I didn't present the numerical results, I should mention that they were very encouraging. So just for the third contribution, before presenting it, let me put a little bit of context to motivate it. So let's say we start with Newton's method. We know that it might be expensive due to the computation of the second derivatives. So an option should be just to drop this part and to have Gauss-Newton. That might be good for zero residual problems, but not that good for non-zero residual ones. So one alternative could be to perform this shift in the eigenvalues of the matrix so that we have a safely positive definite. This is the rationale for Levenberg-Marquardt. So it's a possibility. Another possibility would be to simply adopt a quasi-Newton idea to approximate this Hessian. But in this case, we are just ignoring the special structure of the problem. So one could also apply quasi-Newton, but just to the second order part of the matrix. And in this case, it might be quite expensive because of storage, so that one other idea could be use our sign-free spectral correction for the Gauss-Newton. And another one could be, for very, very large problems, to use diagonal approximations for these two parts. So we not only take advantage of the structure of the problem because of this division of the diagonals, I mean, of these components, and also we have a possibility of approximating the problem with the structure. So this is actually our approach in this third contribution that was developed together with Hassan Mohammad from Nigeria. And we proposed this algorithm that we called Structure Diagonal Hessian Approximation Method, SDH-AM. So the idea here is to assemble two diagonal matrices. In the very beginning, we just start with the identity, and then we compose this diagonal matrix component-wise using this expression. Notice that these vectors, y hat and y bar, they are defined with secant flavors, but with different roles, exactly as they should take part, approximating JTJ and approximating S. These two components must be safeguarded, so we would like to have all the components of the diagonal matrix positive, to have positive definite approximation and distant directions. So the idea of the algorithm is quite simple. The direction is computed in a very simple solution of this very simple system. We use the non-monotone line search of Jean and Hager to control the evolution of the algorithm, combine it with a safeguard quadratic interpolation as in Denis and Schnabel's book. So our assumptions for obtaining the complexity analysis were that the level set of the problem is bounded. We have continuous differentiability of the objective function, twice continuously differentiability, and uniform continuity of the gradient. We managed to prove that the directions are of descent and they are gradient related, and also that the algorithm is well defined in the sense that the line search is finished in finite time. And this is the evaluation complexity result that is aligned with the result for unconstrained minimization. We obtain an epsilon stationary point in no more than epsilon 2 minus 2 function evaluations. This constant here just has algorithmic parameters and constants that comes from the problem. Okay, so just a brief summary on this part. This strategy is completely matrix-free. We just need the action of the transpose of the Jacobian upon a vector, so we don't need to compute to assemble this Jacobian. You just have to know how to perform this product, so that the solution of the system can be done in the order of number of variables operations. The worst case evaluation complexity result says that our epsilon stationarity is obtained with this order of function evaluations. And I didn't also prepare the numerical results in detail, but the algorithm showed very nice results for zero, small, and large residual problems. So we compared, and we have a very competitive performance. So now our last but not the least, and the final contribution. This is our joint work with Roger Belling and Douglas Gonçalves. And in this case, we were interested in analyze the local convergence of Levenberg-Marquardt without the assumption that we have zero residue. So in this case, our set of solution is the set of points which are stationary for the problem. We consider a particular stationary point, x star, define a neighborhood around it, and we are going to use this notation with the bar to denote a point that is close enough to the given x with respect to the stationary points. So our main assumptions are the Lipschitz continuity of the Jacobian and also an error-bound condition upon the norm of the gradient of the nonlinear least square function. So we have assumed all this, not only the Jacobian Lipschitz continuity, but also the error-bound condition in a neighborhood of this x star. So the standard linearization error for the residual function, I just recall it here, and we are assuming we have this satisfied in a neighborhood of x star. Because we are in this neighborhood, we have this boundedness, so that not only the Jacobian, we have to assume the Jacobian Lipschitz continuity, but we have also, as a consequence, the Lipschitz continuity of the residual function and the Lipschitz continuity of its gradient. And we have this condition that turned to be important in our analysis, that is the incomplete linearization error of the gradient, in which we linearize the gradient, but we do not include the second order derivatives part. That's why we call it incomplete. And because of that, we have this with the square, but we have this term here also to take care. A consequence of the error-bound condition, together with this Lipschitz continuity, is this inequality that's also important. Now, because of this remaining term that appears here, we need extra assumptions. So we actually took care of this term with points that are in the neighborhood of x star and a z that is stationary and also is close enough to x star. So we would like to establish conditions that depends on the distance between these two vectors with different powers here. So A3, we have 1, A4, 1 plus delta, delta between 0 and 1, and A5, we have the square here. Clearly, in case we have 0 residue, then, or in case our problem is affine, so that the Jacobian is constant, these conditions are satisfied with the constant 0. But we are interested in problems that have non-zero residue. So that's why we have to accommodate the analysis along this line. So here I just recall the expression for the Levenberg-Marquardt iterate and the local iteration. And we have, in case the rank of the Jacobian is constant in this neighborhood of the solution that we are analyzing, just assuming the Lipschitz continuity of the Jacobian, we obtain this bound upon the Levenberg-Marquardt step. So we just need that. Now, in case the rank diminishes as the sequence approaches this stationary point, then depending on the analysis, depending on the assumption, and depending also on the expression for the Levenberg-Marquardt parameter, we obtain this bound for the direction. So if we have the third assumption, we need to impose that our Levenberg-Marquardt parameter is bounded away from 0. I recall that this constant is the constant from assumption A3, and L4 is the constant from the incomplete linearization of the gradient of the NLS function. And we obtain the bound in this way. Also, under diminishing rank, and if we have the assumption A4 and use this expression for updating the Levenberg-Marquardt parameter, we obtain the bound. And under A5, this is the expression for mu k. So just putting all this together to ensure that we have this bound. In case the rank is constant, just take the Levenberg-Marquardt parameter as the norm of the gradient at the current iterate. Now, if the rank diminishes, then depending on the assumption, and we have different expressions for the Levenberg-Marquardt parameter as well. It's important to stress that our assumption upon the rank of the Jacobian, the rank is diminishing, but it has to be above 1. So it implies that the meaningful part of when we decompose this matrix, the meaningful part of the eigenvalues is uniformly bounded by this lambda underline. So the existence of this lambda underline is implied by this assumption here. Okay, so after that, we have another lemma that provides us the main ingredient for our analysis. And to get from this lemma, we obtain, depending on the assumption and the appropriate choices for the Levenberg-Marquardt parameter, we obtain the contraction of the sequence generated, and then we can analyze the speed, the velocity of the convergence. So under constant rank, if we are with our assumptions originally, if we take the Lagrange, the Levenberg-Marquardt parameter with this expression, then depending on the assumption, we obtain the convergence to the stationary point. The distance of our iterates goes to 0 linearly, superlinearly, or quadratically. So this under constant rank. Now, under diminishing rank, the analysis is a little bit more involving and also depends on the expressions for mu k. So depending on the assumption and the expression for mu k, we obtain linear convergence, superlinear, or quadratic with these expressions here. Okay, here an example with diminishing rank and non-isolated stationary points. You can see here the level sets of our NLS function and the graph of this function. Here in the colors, we see the lot of the zero, the points such that this equation is 0 is here, and the other one is here, so that we have a zero residue problem, a zero residue solution that is here you can identify. And we also have a set of stationary points along this line that can be followed in the graph. And we select this point to make our analysis. So this is the set of stationary points. The distance to these points can be expressed in this way. This is the point we have selected to perform the analysis, the radius, and the non-zero residual value of this nonlinear least square function. So all the assumptions, A1, A2, the initial assumptions are satisfied with these constants. And in this case, A5 is satisfied so that we have a neighborhood of this X star such that quadratic convergence is ensured. Indeed, we can follow and see that we obtain the quadratic convergence starting from this point and just taking the Levenberg-Marquardt parameter in this way, and that's what we have obtained. Okay, so just summarizing this contribution, we have analyzed the local convergence of Levenberg-Marquardt using an error-bound condition, and the basic assumption is that we don't have zero residue. When the rank of the Jacobian is diminishing as the sequence approaches the solution, the choice of the Levenberg-Marquardt parameter shown to be important. And depending on the assumption, we have different choices. As we have already seen in previous slides, this measure actually tells us the effect of the second-order part of the Hessian upon the difference of the point. So it's a combination of nonlinearity and residual size. So to obtain fast convergence, it's important that the contribution of this part of the Hessian vanishes as X approaches to the set of stationary points. And we hope that our study may shed some light in the development of Levenberg-Marquardt algorithms for problems with non-zero residue. So just closing up, The nonlinear least squares problem is very important in many, many applications. Several colleagues commented on that yesterday, and will still comment. There are people that are working with that and are going to present to us. And for us, it's from the point of view of smooth optimization, we also consider this as a possibility for obtaining feasible points. So it's important also. Since the works of Levenberg, Morrison, and Macquart, many research have been performed. If we Google this expression, we will find more than 2.2 million results. So it's really impressive, the importance of this problem. So just summarizing what I have presented in terms of the specific contributions, we have used the spectral ideas to correct the Gauss-Newton model and to assemble this SDA-JM algorithm that address large-scale problems in the structured diagonal matrix-free way. We have also devised algebraic rules for computing the Levenberg-Marquardt parameter, and we analyzed the local convergence of the Levenberg-Marquardt for non-zero residual problems under an error-bound assumption. So to finish, just a small list of references, and I take this list just to acknowledge again my co-authors. So here we have Douglas Gonçalves, Elizabeth Caras, Bernard Zweiter, Hassan Mohammad, and Roger Belling. Thank you very much for your attention.